first of all, I would like to thank the organizers for allowing me to have this opportunity to give this talk here. So my talk will be about some papers that are actually going to that's coming out actually this week and next week, 2 of them. So this has been going on for a while now, which is that we're looking at general constraints on effective field theory coming from the assumption of unitarity in the ultraviolet, and subsequent are results that are derived in some cases phenomenological results that are derived by looking at these bounds. So in other words, this talk has 2 components. First is the positive part, and second is the landscape part. So let me just begin by separately describing what do I mean. So first, what do I mean by positive? So positive, of course we know positive is some number greater than 0. But in this talk, the positivity that we'll be talking about is some geometry that is defined through the positive of some certain values. And actually this is not something new, and we've all encountered it before, and actually we've encountered it in middle school, which is the notion of the center of mass. So in middle school, we learned that if you want to compute the center of mass, you just have these points here, and the position of the center of mass is going to be somewhere inside here. It's given by this formula. So it's just basically each point weighted by the mass. But of course, you can turn this description around and say that, oh, if I want to talk about the region inside here, then you can say that the region inside here corresponds to some center of mass of some configuration, right? For some mass distribution. So in other words, we can describe the inside of some region to be a positive sum of the vectors that constitute your vertex, your vertices. That gives you what you mean by the region in here. So this notion, to make it, since this is about positivity, so that means that we can always rescale things and then maintain positivity. And so it's better to just define this problem in a more projective way. So if we have d dimension, these are d dimension vectors. I'm going to put it into d plus 1 dimension with the top component just set to be 1. Then the same statement is just simply that the inside of this polygon is inside what is called the convex hull, where the convex hull is just a definition that you have a positive sum of these vectors, and the parameters are all positive and they sum to 1. So this is what mathematicians define what is a convex hull. And this gives you a notion of what is polytope. And of course, if these vectors are d-dimension, then this gives you a d-dimension polytope. So we're starting to define a geometry where the definition is through these positive values. So this is just a very simple thing that we've all encountered before. Now, of course, it's more important, I mean, for practical purpose, to not express the polytope in terms of this fashion, because there's a lot of redundancy. This can be arbitrary positive numbers. But really, in terms of the boundary. So of course, when we talk about polygons, it's more easily to talk about the boundary instead of the vertices. So we can ask, what are the boundaries of this polygon? Of course, I can draw it, and we know that BC is a boundary and AC is not a boundary. But let's just imagine you have a problem where you're in 127 dimensions, and you have about 1,000 vertices. How are you going to describe this polytope? And how are you going to describe the boundary? So what characterizes a boundary in this case? And in this case, what you will want to do is let's just use this 2-dimensional example. So what differentiates between BC and AC? Well, of course, we know that BC, all of the inside of this polygon is on one side of BC, so that's why it's a boundary. But AC, some are on one side, some are on the other side, and actually some are along the line here. When it's along the line of AC, then that means that if this A here is somewhere inside that is on this line, that means it's collinear, and therefore the determinant of this quantity is 0. That means that if the determinant of this quantity A on here is 0, that means the sign on here and the sign on here is opposite. So that means that AC, if you take arbitrary point inside AC, some will be 0, some will be positive, some will be negative. But that also tells you that if it's on the boundary, if Ui, Uj is corresponding to a boundary vertex, then taking the determinant, it will always stay positive. So this is how you characterize a boundary. A boundary is such that if you take the vertices, and then you take the determinant will always be positive no matter where you are inside. So that characterizes what is the boundary. And of course, we can generalize this to any dimension. So this is just the 2-dimension case, but if it's 7 dimensions, you just take the 8 by 8 determinant. Okay, so this is basically set up what is called the convex Hall problem, which is that you have a bunch of vertices here, and then you want to talk about what is inside. So what do you need to do? Well, first you need to determine which of these vectors are vertices, and then you need to determine which of the vertices form the facets of this boundary. And remember, in computing, determining what is a facet, what you need to do is you need to take the determinant of a collection of these vertices just to see what their signs are. In other words, this problem is a very difficult problem because this problem grows polynomially with the number of vectors that you have. And actually it grows, you've got n vectors in d dimensions, the complexity grows as n to the d over 2 power. And the cases where this kind of problem appear in physics, generically you have infinite number of vectors. So that means that generically this kind of convex Hall problem in physics is completely unsolvable analytically, because you just have infinite number of vectors and the complexity is just infinite. However, there's a very special class of vector in which not only is this problem solvable, but this problem is completely trivially solved. And that is that, let's say if you have a set of vectors, u, and morally, for this vector you have a preferred ordering. So there's some kind of notion where you can just order these vectors. Good. So if these vector has a property that once they're ordered, their determinant is always positive. So let's say determine ui1, ui2 to uik is positive whenever i1, i2, i3 up to ik is ordered. Then the convex Hall of this set of vectors is called what is called a cyclic polytope. The convex Hall is a polytope, and it's called and if the vector satisfies this condition, then it's called a cyclic polytope. What it's called is not important. What is important is that the boundary structure of this cyclic polytope is completely solved. You already know. Even if you have infinite number of vectors, as long as they satisfy this condition, then you already know what the boundaries are. For example, in 2 dimension, of course, the polygon, then the boundary is just I plus 1, which means that you're just looking at adjacent vectors. For 3 dimensions, you start with 1, I plus 1, infinity. And the 4 dimension is just I plus 1, jj plus 1. You just completely solved. You already know what the boundaries are. And if you're curious why this is the case, or why it's always adjacent, you can just do a very simple example and you'll understand, and also understand what this picture is. So let's just take 1 minute to do this example. So again, let's consider a convex Hall. This is a special point in convex Hall, where I'm just taking the linear combination of u6 and u9 vector, with a and b to be positive. That's what the convex Hall means. So according to here, if I'm in 4 dimension, the boundary should be ii plus 1, jj plus 1. So that means that 4, 5, and 7, 8 should be a boundary of this polytope. So let's just remember, when we have a boundary, that means any point inside A, or any A of B, this thing has to be positive. That's what characterizes a boundary. So let's see if this is actually just positive. So we take a determinant. A is given by a linear combination of these two with positive coefficients. So this splits into 2 determinants. Now what is important is that because these are adjacent, so that means the U6 is just two permutations away to be perfectly ordered. And similarly, U9 is also 4 permutations away to be perfectly ordered. In other words, they're always just even permutations away of being ordered. But you already know that once they're ordered, they're positive. So that means that they're always even permutations away of being totally ordered and therefore positive. And therefore, this thing has to be positive. And that tells you that this is a boundary. Okay. So if you have a cyclic polytope, then this problem is completely trivial. It's solved. So now we're back to physics. So we have this nice mathematical object, which is a cyclic polytope. So now let's ask, do we have convex Hall problems in physics? And second of all, when we encounter convex Hall problems, do we actually find cyclic polytopes? And of course, the reason I put these 2 questions is because both of them, the answer is yes. And at the end of the talk, you'll see it's yes in a very major way. So as an example of where this will appear in physics, so let's talk about effective field theories and low energy effective field theories, or low energy distribution of any system that you have. For an effective field theory in low energy, that means that we're looking at this is just schematic, we're looking at some Lagrangian that has an infinite number of higher dimensional operators with certain coefficients that are completely unfixed and depend on the precise information of the UV physics. Now, of course, since we have a Lagrangian and low energy, that means we can always compute physical observables. So we can compute the for example, the 4-point amplitude. And so that means that in infrared, because of this structure here, the infrared, the 4-point amplitude as a function of S and T Mandelstam variable is going to be given by something that has massless modes, and then you're going to have a polynomial expansion. For this polynomial expansion, the coefficient of this polynomial expansion is directly linearly related to the couplings of your higher dimension operators. So let's look at these coupling in more detail. So we can look at the 4-point amplitude and just consider it as an analytic function in the complex S-plane. So the analytic property of this amplitude, even though you don't know what the UV completion is, you already know what the analytic property is. As long as you have t weighs t much smaller than 1, then there's not going to be any threshold singularity. So all the analyticity, the non-trivial analyticity is going to happen on the real S axis, where you might have poles and branch cuts. So you already know this. So we can consider a contour integral. Let's write down the contour integral here, where we integrate the function. Even though we don't know what the function is, but we just say that we have a putative function, which means that we're assuming that there's a UV completion where where the notion of amplitude still exists in high energy. So if we have a complete function MST here, even though we have no information on what exactly it is, we do know that when we do this contour integral, first of all, by Froissart bounds or unitarity constraints, you know that this integral will vanish because of how this amplitude behaves at S infinity. So this integral is just going to be 0 on this side, because here the contribution is just 0. Now what this is going to pick up is that at the origin, it's going to, because of the fact that even though you don't know what MST is, you already know that in the origin, at low energy, you're going to have massless pole and polynomials. Therefore, this integral is going to, these polynomials is going to induce simple poles at the origin. Therefore, this integral is going to pick up these coefficients of your higher dimension operators here from the fact that you have these S factors that create simple poles. On the other hand, you're also going to get contribution from the discontinuities. And you already know that from the poles and the discontinuities, you know that it's going to be positively expanded, the pose is going to be positively expanded on the Gegenbauer polynomial or the Legendre polynomial in 4 dimensions. And the discontinuity, you can also prove that it's also given by expansion on the Legendre polynomial. Now, what I mean by positive expansion in this coefficient here is just, for the residues, it's just the square of the 3-point coupling. For the discontinuity, it's just going to be the spectral functions, which both of these are positive. And I mentioned the word positive, then that means that you're relating the low energy coupling to something that has a positive behavior. So you're having this non-trivial information, because you're relating what is happening here to here, because the contour infinity vanishes. Now this is a very nice formula. However, this formula, in some sense, you can say this is a completely useless formula, because we're having equations, but these are the things that we're interested in. We have these coupling constants that we're interested in. However, here you have information about the spectrum, and the spectrum, you have no idea what the UV completion is. We don't know how the standard model is completed in the ultraviolet. So in principle, you can have infinite number of particles. We have no information of MA here. We have no information about the mass. We have no information about the spin of the particle. So you say that there's an infinite number of unknowns here. This is just a completely stupid, useless formula. However, it's not stupid because the fact that this is positive. And that means that there's this hidden positive geometry that it existed. So let me just, to make this geometry more clear, so we're simply identifying, so this formula is telling you that the low energy coupling, it must be given by a positive sum, so you can do a Taylor expansion here because this is a Taylor expansion of low energy. So it must be given by a positive sum of these factors here, where XA is just the 1 over mass squared, and then V is just the Taylor coefficient you get from expanding the Legendre polynomial, or the Gegenbauer polynomial. So you basically have this non-trivial formula. And so the first comment I want to make is that this non-trivial formula tells you that this is a convex Hall problem. How do you see that? So let me just organize this formula to make it transparent. So here I'm organizing all my higher dimension coupling. So this depends on, so of course this is coming from here. And 1 over m to the 4 means that how many powers of suppression of mass that you're getting from here. And this is meaning how far away from t that you get. So for example, for fixed mass dimension, so let's look at 4 derivative operators. So we can collect these coefficients into this vector. Then this formula tells you that this vector is given by a positive sum of the vectors that you get from expanding the Legendre polynomial. In other words, this is already telling you something non-trivial, that the higher dimension operator in your putative effective field theory must live inside of some polycomb. This is, first of all, this is a non-trivial constraint. However, this, as I mentioned before, once you have polytopes, this can be a stupid constraint because you have no idea how to compute the boundaries. If you don't know how to compute the boundary, then this is just something that is very stupid. However, the point I want to state is that this is actually, okay, before, oh sorry, I should step back. So this is just telling you that indeed we have a convex Hall problem. So basically, and in fact, the convex Hall is given by two geometry. One is coming from the expansion in T, which is reflected in the expansion of your Gagenbauer polynomial. And the other is the expansion in terms of the propagator, because all of these singularity and discontinuity is coming from propagator. So there's also expansion from a propagator. So in other words, this geometry is a reflection of unitarity and locality. So we do have a convex Hall problem. The second is, do we find a cyclic polytope? And remarkably, this is why nature is so remarkable, is that actually somehow nature just decides to give us a cyclic polytope. So let's just collect these vectors here. Remember, these vectors are coming from the expansion of your Legendre polynomial, expanded around 1, which is the forward limit. What dictates that it's a Legendre polynomial? Lorentz invariance. Lorentz invariance tells you that these discontinuity can be expanded on Legendre polynomial. So here, these are the expansion coefficients. So the first thing that you note that is obvious in this expansion coefficient is that all of these are positive numbers. Okay, so this is just some function that you have here. For somehow the function, if you take infinite derivatives, it's always just positive numbers. Not only is this positive, if you take this matrix and you just take any random minors in here, it's all positive as well. This is remarkable. Okay, if you remember, when you're taking determinants, you're taking plus, minus, plus, minus, plus, minus, and somehow you take these numbers and you just crunch it through, you realize that actually they're all positive. For some reason, and the reason that you get these numbers is coming from this special function. And as I've said before, if all of the ordered determinants are positive, that means that you have a cyclic polytope. So nature actually gives us a cyclic polytope. And this cyclic polytope is a reflection that our world is a Lorentz invariant world. And you can also, before I was talking about Legendre polynomial, this is actually not just Legendre polynomial. If you're looking, because Legendre polynomial is about scattering of scalars. If you want to talk about scattering of spinning states, for example, photons or gravitons, then you just need to change Legendre polynomials to Jacobi polynomials. And these are the coefficients that you get from expansion of Jacobi polynomials. And actually, of course, first we notice that all of them again are positive. And once you order, they're actually the determinant is also positive once the spin are ordered. So this is not just for Legendre polynomial. This is for the class of functions that are given to you by Lorentz invariance. So back to the convex Hall problem. So remember that I said that these high dimension operator coefficient must live inside the convex Hall of these vectors. If I just told you this information, in principle, this is a useless information because these vectors are there's infinite number of them, so there's no way you can, no matter how big a computer you have, there's no way for you to really compute the boundary of this convex Hall. However, because of the fact that we know that these vectors form a cyclic polytope, we know exactly what the boundaries are. And since we know exactly what the boundaries are, that means that you can get non-trivial constraint because all of these higher dimension operators must sit inside this boundary. And you can visualize, even for low dimensions, you can visualize this constraint. So for example, this is the condition for 4 derivatives. So the two 4 derivative coefficient must live inside the boundary here, the bounded region here. And this is the region that is carved out when you have 6 derivatives. So in other words, here we're giving you a constraint on your low energy higher dimension operator, where this constraint just only assumes that your UE completion satisfies both Lorentz invariance and unitarity. In other words, not all effective field theories are consistent. Okay, and in fact, it's actually pretty hard to be consistent because if you really look at the scale of the region that is being carved out, that is allowed here, this scale is really very small. So, okay. Now previously I was just talking about the constraint that is coming from the expansion of the Legendre polynomial. We can also talk about the constraint that is coming from the expansion of the propagator. And that reflects it, and that means that instead of organizing your higher dimension operator in terms of mass dimension, you're organizing it in terms of how far away are you expanding in the forward limit. So if I collect, for example, these 3 sets of coefficients, then these corresponds to the different mass dimension coefficients, but they're all expanded to the first degree away from the forward limit. Then reading from this equation, then it tells you that it's also given by a convex Hall, but it's given by a convex Hall of this form, where M again is the mass of your spectrum, and you don't know what the spectrum is. However, because of the fact that it's coming from a geometric series, this tells you that this is actually convex Hall on the points of a moment curve. So this is a one-dimension curve in d-dimension space, because it's one dimension because it's a curve, and it's just one parameter. But each component is just different moments. And of course, this satisfies this behavior. So that means that if you collect these higher dimension operators in this form, they must live in the convex Hall of points on the moment curve. And what is the condition for that? We've proven that, there's also mathematical, we've proven that basically what this means is that if you take the higher dimension couplings and you order in this fashion, what is called a Hankel matrix, where you have 1, G1, G2, G3. This is G1, G2, G3, G2, G3, G4. So this is a symmetric matrix. If you order in this symmetric matrix form, then if you take a determinant, then this matrix has to be positive. Okay, so this positive condition tells you that these higher dimension operators are coming from the convex Hall of this moment curve. So there's two positive geometries. Okay, good. So now let's do phenomenology. So let's look at what implications that you can have. Well, actually previously I already showed you that there's non-trivial implications where you are already bounding the higher dimension operator. But let's just look at explicit models. Okay, so let's go to 3 dimensions for technical reason. This is actually the most easiest thing that you can do. So let's consider in 3 dimensions. So in 3 dimensions, in low energy, you're just going to have gravitons and photons. All the charged state, all of this are integrated away. And so you basically have an effective action that includes the Riemann Einstein-Hilbert terms f squared plus all the higher dimension operators. For example, for the leading higher dimension operator, you will have an f to the 4 term. And the f to the 4 term, this c here, in principle is a coefficient. This coefficient contains the information of the massive states that you're integrated away. So generally people tend to organize this c as powers of z, where z is basically the charge to mass ratio of the particles that are being integrated away. Okay, so this is just the leading piece. Of course, there's going to be an infinite number of them. And just to show you an example of what these function coefficient looks like, so this is when you have a scalar that is integrated away, and when you have fermions that are integrated away. Okay. Okay, and of course the point is that we can get, first of all, we can get non-trivial information by really doing the integral. So we can compute the one loop amplitude and do the large mass expansion. Once we do the large mass expansion, we can do it to arbitrary orders, and then this gives us the coefficients of these higher dimension operators beyond f to the 4. So basically the same is that we have the coefficients for a higher dimension operator arbitrary order in our theory. And just to show you that, so this is the leading order 7/8 coefficient. You can see it appears in the amplitude here. So basically we can reproduce all the numbers for any derivatives that we want. Good, so now let's impose our constraints. So since we already have all these higher order coefficients, we know that locality tells you that the Hankel matrix must be positive. So that means that you just take this computation here, where we do the one loop amplitude and just expand the large mass. We collect the coefficients, and then we organize in this Hankel matrix. And so you see, so this is just schematic. This is just to show you what you do. You just put the coefficients in here, and then all you have to do is just press enter, compute the determinant, and that requires that this thing has to be bigger than 0. So you see that the result that Mathematica tells you is that it's putting bounds on your z. So the charge, this is telling you that the charge to the mass ratio has to lie in a certain region. So let's just, so of course you can do bigger, 2x2, 3x3, 4x formation, and just impose a bound. So at 60th derivative order, which means that we include the higher dimension operator to 60 derivative order, this is the bound that we get. So we get 2 allowed regions. Either z has to be between 0 and 1.14, or z has to be bigger than 124.28. So that means that the leading charge to mass ratio piece that you're integrating away has to live within these 2 regions. If it's outside of this region, then you're violating locality of the UV. Now, these 2 regions are actually somewhat different. Because remember, we're at 60 derivative order, so you might ask that how is this number behaving as you increase in derivative order? So this is a plot of how this bound is behaving in terms of derivative order. So first, for the number A, you'll see that here, this is just asymptotic to some fixed value slightly outside of 1. Whereas for B, in terms of the row, you see this is just a linear raising, number. So if I trust my extrapolation, which one can doubt, but if I trust my extrapolation, then I would be saying that this region is going to be completely ruled out because this is just a linear rising function going to infinity. So this is going to be completely pushed away, and really my z is just confined in this region. It's something somewhere between 0 and 1 point, and somewhere above 1. So you might ask, this is weird, because for those of you who are familiar with this kind of discussion about the weak gravity conjecture, the weak gravity conjecture is telling you something opposite. It's telling you that the weak gravity conjecture tells you that there must be a charged state that has z bigger than 1. We're actually saying that in 3 dimensions, when you're looking at this problem in this format, you actually see that it seems that charged states must lie between 0 and 1. And not only is this weird, this just contradicts with our standard model, because you can imagine this 3-dimension theory as compactification of our standard model to 3 dimensions. And in our standard model, the leading piece of z is given by the electron. The charge to mass ratio normalized by n price is given by around 10 to the 22. So this obviously violates this bound violently. And so what's wrong? So this must be something that is wrong. And it's not that something that is wrong. It's just that in 3 dimensions, when we're computing these coefficients, you notice that, so this is what is different than 4 dimension, for those of you who are familiar with the 4-dimension computation, is that these coefficient is actually dressed with the mass. So that means that the leading contribution is the largest z, is going to be a leading contribution, plus the smallest m. So it's actually there's actually a competition between the lightest state and the largest z. So we can deform our bound, so we can include the lightest state by including this parameter beta here, where beta is basically the electron to the neutral state ratio, where this neutral state is the lightest neutral state. And you'll see that once you turn down non-trivial beta, this slope starts to go down. And therefore you see that the slope starts to go down, and you can plot the slope with respect to beta. And this appears that the slope is as you crank up beta more and bigger, that this slope starts to go at asymptote to 0. So that means there is some beta critical here that allows this large z region to survive. So that means that in 3 dimensions, there's an interplay between once you have a charge state with the z factor that is very large, then it's requiring you to have a neutral state, in which the neutral state have a mass that is parametrically much more smaller than the state that was giving you the large z. In other words, the neutrinos in the standard model save us from unitarity, because the neutrino is actually the light state that is giving us the contribution that it contains this linear raising function. So since in light of time, I'm going to skip the next one, which is a discussion about, there's also another way of saying this scenario, which is to have other charged large z states, which are equal mass distribution away. But anyway, so just by looking at this impose non-trivial bounds. So this tells you that in order for us to have a charged state with z much greater than 1, we must either have neutral states where the neutral state mass is smaller than the charged state, or parametrically smaller, or that we must have closely lying charged states. And you can see that you can consider various perturbative string theory, and indeed in various cases where they have cases where they generate these large z states, either one of these are satisfied. So in light of time, I'm just going to talk about this in 1 minute. So there's another way of using these constraints, which is to talk about really scanning what we call the string landscape. And so what is the difference between the unitarity bounds I talked about and what if you have a string theory? The difference is that you have a world sheet. So for example, you can think about, let's say if our theory is coming from compactification of an open string, compactified to R4 times some compact surface. Then that means that the world sheet CFT is going to give you by the free boson and some compact CFT. The fact that you have a free boson means that for those who went through Koczynski, knows that you're going to have a Kopa-Nielsen factor, and that tells you that the scattering amplitude is going to satisfy non-trivial monodromy relation. These non-trivial monodromy relation you can expand in alpha prime, then relates to higher dimension coupling. So for example, and generically, we just organize our higher dimensional coupling constant here. And because the fact that you have monodromy relation, you see that independent degrees of freedom are actually much more smaller. Then on top of this, we can impose our unitarity like the Henkel matrix constraint. And this is the region that you will carve out. So up to 6 derivative order, you really only have 2 parameters here, G30 and what we call G10. These are the only parameters that is allowed, free parameter that is allowed from the monodromy relation. And then we impose unitarity constraints. So these different regions are the regions that are carved out by the different unitary constraints that I talked about before, the Henkel matrix constraint and the Poitou matrix constraint. And you see that they're mostly mutually exclusive. And the only allowed region is actually this tiny region here, this little intersection here. So I enlarge this section. So this is a section, and so look at what this is here. So this is the reflection that you have an open string behind this theory. And notice where the fast space string theory lives. It lives right at the boundary of this region. So this is where, so this is, in some sense, this is an on-shell. So in talking about string landscape, this would be an on-shell way of talking about what is a string landscape, talking about what are the allowed regions in the higher dimension couplings that is dictated by string theory. So in other words, I would like to put it another way, that string, from this, just this little tiny region, you can say that string theory is very predictive. Okay, so in summary, so really, as I showed, the union of physical principle in terms of unitarity and locality and symmetries in the UE actually defines in the IR in the form of a positive geometry, which is these polytopes. And these polytopes impose constraints on the space of coupling constants in the EFT. And I could present you with 2 explicit examples of how these constraints, what these constraints can tell us in terms of charge to mass ratios, and in terms of provide you a way to start discussing carving out the string landscape in an on-shell way. And so, and there's also further analysis that, of course, this is just really the very beginning, and there's really lots of things that you can do. And of course, one of the primaries is really look at how these slopes behave at high derivative orders. You can look at multi-U1 cases. You can look at the case where you had involved a gravity photon. And of course, the fact that nature gives you something so beautiful puts you to ask that is there more type of this kind of positive out there? And quite remarkably, the answer is yes. Well, not remarkably, but interestingly, the answer is yes. So for example, exactly the same structure appeared in planar Ising network. So when you talk about the 2-point correlation function of a planar Ising network, it was realized just this summer that is described by a positive Grassmannian, and exactly this kind of positive geometry. So for those of you who are interested, this was first discussed this summer by Galashan, and we had a follow-up paper which is going to come out in PRL actually on Friday, and that really discussed how exactly the same geometry appears in the discrete system, I remind you, in the planar Ising networks, and where this is not just a symmetry. This is not just a new structure, but actually it's a useful structure because just to do a commercial. In that paper, we actually computed a lattice. Using this structure, we computed a lattice that has 10 to the 9 lattice site. Just very simple on a laptop using this structure. So the same structure is appearing in discrete system. And also, this is the same system is also appearing in the geometry of a CFD bootstrap, which is a paper with NEMA that we just submitted and is going to come out tomorrow morning. So it's a busy December, we all know. So, and of course, we expect that there's much more yes waiting to be discovered. So thank you very much.
Well, okay, so I'll do questions. Any questions?
I'm a little confused about the analyticity argument that you made near the very beginning. Aren't there cuts that come all the way down to the origin when there's
So this is there's 2 things that one can do. So first of all, of course, we can assume that the unique completion is such that the massless degrees of freedom are still weakly coupled. So that means that there is a weak coupling that you can separate between the massless cuts and the poles. So in other words, that would mean that you're assuming that there's an M string is below M Planck. So that the amplitude is UV completed before M Planck becomes large. So this is one way. And the other way of dealing with the massless cut is to not expand in S and T, but expand in S and angle, because these cuts are are always coming in the form of log S over log T. And so and T is really S times 1 minus cos theta. And so if you expand instead of not in terms of S and T, but in terms of S and angle, then there's actually no cut in S, but the massless cut goes away. So there's various ways to deal with the masses cut, but basically the way to deal with it is separate from the discussion.
Suppose I'm not interested in all this fancy operator, but then I just want to G-2. I want to know 10 loop level itself. How far will you able to tell us some real calculation?
To calculate the G-2 at 10.
10 loops, 2 loops.
Well, I mean, well, this will be a separate talk, not about this, because we have, of course, one of the things in here is that we were able to do these constraints on the photons, and precisely this formalism where we do the constraints on the photons, which as I said here, that we can talk about photons at graviton. Precisely this formalism you can use to compute the G-2, because it just in terms of how much it streamlines. The computation that we did it in this paper, that the computation for the G-2 at one loop took 2 lines, and compared to the general QFT books where you have more than 1 page and we're moving around gamma matrix. The computation of G-2 using this Amschel formula just took 2 lines in the paper. So of course we didn't go and start computing the 10 loop, but yeah, so there's applications.
You say it's feasible.
Yeah. Well, I mean, it makes things simpler.
Well, okay, so I think we'll end up at the right time for coffee break. Okay, so let's thank all the speakers.
Thank you very much.